Niyanig ng magnitude 5.0 na lindol ang Batangas.
Nasa state of calamity ang bayan ng Mabini sa Batangas.
Natupay ang epicenter ng lindol, 9 na kilometro.
Niyanig ng 4.5 magnitude na lindol ang Mabini, Batangas kaninang 1:25 ng hapon.
In the quiet town of Mabini, Batangas, life unfolded at its own gentle pace until an unforeseen catastrophe struck, altering the course of its history. Located just 5 kilometers away from the island of Tingloy, Batangas, Mabini lies dangerously close to a fault line, a geological feature that would soon prove to be the source of an unprecedented chaos. On April 9, 2017, at 3:07 p.m., the Philippine Institute of Volcanology and Seismology, or PHIVOLCS, recorded the first tremor near Mabini, registering a surface wave magnitude of 5.6. Just 2 minutes later, at 3:09 p.m., another earthquake jolted the region, this time striking Talaga proper Mabini with an even greater intensity measured at a surface wave magnitude of 6.0. The impact was swift and devastating, with the tremors giving damage to the community. Among the areas hardest hit were the residential buildings in Barangay Bagalangit. Their once sturdy houses, now marked by the unmistakable cracks of destruction. Greetings everyone, and welcome to today's inspection adventure. Today, we're embarking on a journey through the saddle landscapes of structural integrity as we compare and contrast two houses that survived the 2017 twin quakes. Our goal? To understand the stories told by the cracks on their surface, showing us the passage of time, how they were built, and how they've been cared for. Despite the earthquakes having occurred, we will begin our inspection by addressing the 12-point questions provided by PHIVOLCS to evaluate the seismic resilience of these buildings. This assessment aims to understand why these structures remained intact following the twin earthquakes. By following PHIVOLCS guidelines, we'll gauge the earthquake preparedness of these buildings and uncover the factors contributing to their structural stability despite the seismic events. After assessing both houses using PHIVOLCS 12-point questions to determine earthquake readiness, House A scored 6 points, while House B scored 8 points.
House A's lower score suggests potential stability in its earthquake preparedness. It may lack certain structural reinforcements or maintenance measures necessary for withstanding seismic activity.
On the other hand, House B's higher score indicates a better level of earthquake readiness. It likely possesses more robust structural features and maintenance practices, contributing to its ability to withstand seismic events with greater resilience. House B's superior earthquake readiness, as reflected in its higher score on the assessment, can be attributed to the fact that it was constructed by professionals. This professionalism encompasses various aspects of the building process, including design, construction, and maintenance. Professional builders possess the knowledge, skills, and experience necessary to ensure that structures are built to withstand seismic activity effectively. They adhere to building codes and standards, employ proper construction techniques, and use high-quality materials to reinforce the building's structural integrity. As a result, House B likely incorporates robust structural features and maintenance practices that enhance its resilience to earthquakes. This may include reinforced foundations, strategically placed load-bearing elements, and measures to mitigate the effects of temperature fluctuations and setting.
Overall, the difference in earthquake readiness between House A and House B underscores the importance of professional construction practices in ensuring the safety and durability of buildings, particularly in earthquake-prone areas. Investing in professional expertise can significantly enhance a building's ability to withstand seismic events and minimize structural damage.
With the seismic assessments providing valuable insights into the earthquake readiness of each house, we now turn our attention to another critical aspect of their structural health: the visible and observable cracks. These tangible signs of wear and tear offer a glimpse into the structural integrity of the buildings, shedding light on potential weaknesses and areas in need of attention. As we venture forth into our inspection, let us delve deeper into the stories told by these cracks, seeking to understand their origins and implications for the overall stability of each house.
House A exhibits a variety of cracks, each with its own story to tell. As we examine its walls, we can see numerous hairline cracks, delicate fissures that are barely visible to the naked eye. These hairline cracks often result from minor settlement or shrinkage in the building materials, such as concrete or plaster, and can also be caused by temperature fluctuations. Over time, these small cracks can worsen due to the continued stress and strain on the structure. Additionally, we observe temperature and shrinkage crack in certain areas of House A. These cracks typically appear as thin straight lines and are often the result of the natural drying process of materials like concrete or mortar. As these materials dry, they shrink slightly, leading to the formation of cracks. Temperature changes can worsen this process, causing expansion and contraction that further stresses the building materials and creates cracks over time. Lastly, there are diagonal cracks visible on some surfaces of House A. These diagonal cracks can be indicative of structural movement or settling within the building. They often occur at angles and may be more pronounced than hairline cracks, suggesting a more significant issue with the building's foundation or structural supports. Possible causes of diagonal cracks include soil subsidence, inadequate foundation design, or seismic activity.
Shifting our focus to House B, we notice a different scenario. Unlike House A, House B primarily displays hairline cracks. These fine cracks are visible across the surfaces but appear to be the extent of structural damage observed. While fewer in variety compared to House A, these hairline cracks still warrant attention to ensure they don't escalate into more significant issues over time.
Based on the inspection, earthquakes can cause severe structural problems in small or large buildings and affect the structural integrity of columns, beams, shear walls, and load-bearing walls. Once the structure has been damaged, it will either have to be repaired or demolished depending on the level of damage.
While structural damage is relatively common in larger earthquakes, non-structural damage can occur during mild earthquakes. This includes interior walls, electrical items, and various services in the building. Repairs needed after a mild earthquake may include patching up various cracks that have appeared in drywall, the restoration of broken windows and doors, ensuring all electrical wiring is working, and ensuring gas and water pipes are in working order, among others.
Once the structural damage assessment has been completed and the repair can go ahead, it will likely include the following fixes: removal of old masonry and the rebuilding of walls with fresh mortar, the reinforcement of mesh and crack walls, which are then fixed with spikes and cemented over, and the sealing of large cracks with an epoxy-like material.
These two homes have suffered during an earthquake, and we've assessed that the structural problems can be fixed. In that case, investing in preventative measures to ensure maximum safety is a good idea. Two of the most common are:
First preventative measure is seismic retrofitting. This is a modification done to the existing home or structure which ensures they are more resistant and sturdy during varying degrees of seismic activity. So, now that we know the possible structural damages during what generally needs to be prepared after a devastating earthquake, we're now aware what various preventative measures should be taken to ensure maximum safety.